Okay, welcome back everybody to Math 131. We are at Lecture 5. Does that mean we're about a third of the way through the class? Goes pretty quickly in summer school, doesn't it? Today, we're actually going to take two problems that this group had questions about from the homework and look at what they did to see if we can figure out where the mistake is. Then we're going to finish covering section 1.3 and 1.4. We did 1.3 yesterday a little bit, but in section 1.3 they try to introduce you to the limit definition of the derivative, but at that point you really hadn't learned how to do limits. This book likes to give you a little flavor of what's going on to get you motivated and excited, and then the next section they tell you about it. So I'm going to combine the limit definition of the derivative with section 1.4. We're going to learn how to find limits, and then I'm going to do the limit definition of the derivative. A test will always have a question that says use the limit definition of the derivative to find. So you want to make sure that you're good at that. Okay, then section 1.5, we're going to talk about given a function at a particular point, is it continuous at that point? And the word here is differentiability. That means does the derivative exist at that point? Does the derivative exist at that point? When you hear the word derivative, what are we thinking, everybody? Slope of the curve at a point.
Slope of a tangent line.
Slope of the tangent line to the curve at a point. So when we're trying to determine if a function is differentiable at a point, we're going to be thinking about the tangent line to the curve at that point. Does it exist? Because if you can't put in a line that best fits the curve at a point, a best fit line, which is a tangent line, then it can't be differentiable there. So differentiability is a big word, long word, lots of letters, but it just means does the derivative exist at that point? Okay, so can we put in a line of best fit, a tangent line? And then section 1.6, which actually I'm going to sneak in before I get to 1.3 and 1.4. More rules for derivatives. Yesterday you had the variable x raised to a power, the variable x raised to a power, and we took the derivative. I actually slid in a couple more rules yesterday that I didn't point out to you were rules from section 1.6 when we had something like y equals 3x. Y equals 3x. What's that derivative? Y equals 3x. 3. That's just a straight line. The slope is 3. The line and the tangent line are the same. What about the line y equals 7? 0. When you have a constant, the derivative is 0. So I sort of slid in some of those rules yesterday, stretched your brain on that. But the new rule will be general power rule, a very big rule, absolutely necessary for success. And I'm going to actually slide that in as soon as we answer a couple homework questions. Okay, the first homework question that was given to me was from homework 1, and I pulled it up on the screen, homework 1, and I have the work here that we'll go back and forth between the question. And what we want to do is I'll identify what the mistake is. All right, so we'll go to the screen, the internet here, so that we'll see what the question is. Homework 3? Okay. And I really don't think there's randomized numbers in this question, so everybody has the same question this time. Sometimes the numbers are randomized. Okay, question 3 says, a person deposits $500 at the end of each quarter in an account earning 6% compounded quarterly. Can you see that, everybody? Mm-hmm. Okay. And it is my advice for success that you sort of draw this out on a number line to help you come up with a difference equation so you don't make mistakes. So on this paper, what I would have done, somewhere on this paper, I would have said a person deposits $500 at the end of each quarter. That's something that's going to happen quarter after quarter after quarter. So, you know, we're going to use difference equations when the same thing is happening over and over and over. So the end of a quarter, that's 1/4 year, right? Time is 1/4 of a year, which also means n is 1 because we're talking about quarters. And so we're going to make a deposit of $500. So at the end of every quarter, we're going to add $500. The account earns 6%. That's an annual interest compounded quarterly. So it's 6%. You already got that up here. Compounded quarterly. Okay? How much is in the account at the end of 20 years? Keep in mind that N represents quarters. All right, so the person who gave me this work wrote this down as the difference equation. Can you focus? Can you guys see that? Yeah. Y sub n plus 1 equals y sub n times 0.06 times 1/4 plus 500. All right, let's go to how we come up with our difference equation. Remember, we have a y sub n. We have a y sub n plus 1. This difference equation describes what happens every period, one period to the next. Somebody help me out here. So y sub n plus 1 will be what?
Y sub n.
Plus. And what's this part right here? The interest. So what's missing in the difference equation? We got to start with the y sub n. So y sub n plus 1 is equal to, start with your y sub n, then your interest on y sub n, which you did perfectly, y sub n times 0.06 times 1/4, and then you're going to make your deposit of $500. So your 0.06 divided by 4 is 0.015, I think. So 1 y sub n, is that right?
Yes.
Okay. So 1 y sub n plus 0.015 y sub n plus 500. So 1 plus 0.015 y sub n plus 500 is the difference equation. So my advice would be, when you work one of the problems, I'm a visual person. My guess is many of you are visual persons. You need to get the pattern of what's going on here, and then your difference equation describes what happens from quarter to quarter somewhere down the line. Everybody got that? Okay, so that's where the mistake was. You didn't have your y sub n. That makes sense now. And then one more thing I want to point out was, well, of course, for your A, you did have 0.015, which we know that's not correct now because your A is 1.015. And then here is raised to the 4t. Actually, t is 1/4. You mean 4 times how many years it's going to be there, right? T, in your interest equation, it's PRT, T represented in terms of years. When I asked you about this question, you told me the right answer, but I just wanted to make sure the symbols here are not confusing. It is 4 times a year for 20 years. So 4 times 20 is 80. So that is 80. So you'll be looking for y sub 80. So your N represents 80 quarters, which means that your time in years is 20 years. Everybody got it? Okay, ready to go with that problem again? All right, good, thanks. Okay, the next question, we'll close this one out, came from, already lost it, derivatives and tangent lines. Derivatives and tangent lines, and it's question number 5. Was it question number 5? Oh, I got it right here. Question number 5. Okay, it's the last question. All right, so I definitely see why you had a little question here. Now, these numbers are randomized because your question had different numbers than what I have. All right, we want to find the equation of the line tangent to the curve at y equals x cubed at x equal to 2. All right, now because you've already done part of your work, which I greatly appreciate, we're going to use your numbers to keep going. Everybody's going to have different numbers. All right, your question was y equals x cubed at x equal to 1. Okay, using this tangent line. So we were supposed to first write the equation of the tangent line. And I'm going to go to her sheet. She wrote the function y equals x cubed. In order to write the equation line, you got to have a point. So when x was 1, y is 1. So the point is 1, 1. The particular problem I have here, the point is going to be 2 what? 2, 8. Right, when x is 2, y is 8. So I'd have, in my particular problem, I'd have the question 2, 8, the point 2, 8. All right, so once you found your point, you knew the derivative gives you the slope of the curve, slope of the tangent line, so she took the derivative. The derivative with x is just the formula to give you the slope anywhere. If you want it at 1 in particular, you have to put 1 into the derivative, and so your slope is 3. Then she wrote the equation of the line perfectly. All right, this is the equation of the tangent line to the curve. All right, now let's get a visual on this. Y equals x cubed looks like this. And we found the point 1, 1. And now we have the equation for the tangent line. Okay, and this is y equals 3x minus 2. All right, now it was the rest of the question that was the problems here. Find the approximate value of, and in her case it's 0.9 cubed. All right, on my little thing up here it's saying find the approximate value of 2.03, and you're using your tangent line. Okay, so here's the story. We know when x equals 0.9, the real y value is 0.9 cubed, correct? Because the function is y equals x cubed. All right, so the real y value is 0.9 cubed, which is 0.729. 0.729. All right, now what the problem is saying, okay, it's easier to work on the tangent line because the arithmetic is easier. We're going to use the tangent line to approximate 0.9 instead of putting it in 0.9 cubed. So it says use the tangent line to approximate what it is. And if you look, 0.9, well, my graph's not all that great, is it? But if this is 1 right here, 0.9 is very close to it. 0.9 is very close to it. So here is the real y value, but we're going to come on this green line, and you see that green line is going to touch it very close. It's going to be very close to it. So we're going to get the y value off the green line, which is the tangent line, instead of the real y value off the red. So it's called tangent line approximations to the curve. That's what it's called. All right. I don't think your book calls it that, but that's what it's called. Okay. So we're going to take the equation for the tangent line. So let's do that in green since I already have a green tangent line. All right, so here's the tangent line. I'll write it f of x equals 3x minus 2. Let's find the value at 0.9. So we're going to estimate what the y value for 0.9 is on the red curve by using the green line. Okay? So we'll have 3 times 0.9 minus 2. And so we have, I know we should be able to do this in our head, but, you know, hey, the brain's off. Okay, and I get 0.7. So using the tangent line to get the real y values very close to 1 will give me a pretty good approximation of what the y value on the curve is. Okay, and we're off tenths, hundredths, thousandths, 29 thousandths. This is the real answer. Tangent line approximation tells me it's 7/10. I'm off 29 thousandths from the true value. Does that help? All right. So that's a great little insight into some help the tangent line to the curve will give you. Okay, some tangent line approximations. All right, are we good? Okay, we'll pick up again tomorrow with some more questions. And so I appreciate that the people who contributed here had this written out and I thank you for asking. All right. So we are now, yes? Yes, ma'am. You may have your notebook back with all the red writing all over it, and if you'll pass that down, please. And we'll do a couple more at the beginning. And I do appreciate that you were willing to put that up. All right, so I wanted to start out with a quick review of our rules for derivatives, and I'm going to slide in section 1.6 real fast on you, and then we're headed back to 1.3 and 1.4. All right, so I just call this a warm-up. Find the derivative. Okay, don't yell out the answer too fast, although I know you already know it. So we're going to find the derivative. All right, f of x is equal to 5x to the 10th. I'll ask you in 2 seconds what that is. Okay, make me feel good. What's the derivative? 50x to the 9th. You had a constant times x to the 10th. So if you put in all your steps, it's 5 times. Bring the 10 down, rewrite, decrease by 1. 50x to the 9th. Okay, I want you to look over at your neighbor's paper, and I want to make sure that they put in proper notation. You could either say dy dx or f prime x. Here's the red pens. You circle your neighbor's paper so they don't lose points, and they should thank you. Circle those papers. All right. Now, I am going to page 109. Page 109 in the textbook. These are some more rules for the derivatives. And I want you to look at the rule that I slid in on you yesterday. Hey, you need to send that red pen on to the back. Keep that red pen moving. I saw people didn't have it just right. And on the test, when you do your notation just right, you just say, thank you, Ms. McCollum. Don't forget little thank you notes all over the test. I'm so thankful for this question and, you know, all this. Okay, I slid this in on you yesterday, and you just did this rule. This is from section 1.6. It says whenever you're taking the derivative of a constant times a function. So we, in our example we just did, was 5, and my function was x to the 10th. Do you see the rule? 5 times x to the 10th. Then the rule is it's the constant, which was our 5, times the derivative of our x to the 10th. So you just did this rule beautifully, except you didn't use good notation. So if I'm trying to match it up to the rule, this is the k, this is the f of x, because x to the 10th is a function. So if I have k times f of x, the derivative will be k, here's the k, times the derivative of that x to the 10th, 10x to the 9th. All right? Aren't you glad you could do the rule? Alrighty. Okay, next example. F of x equals 3x plus 1. I want you to find the derivative. Okay, what is the derivative, everybody? 3. 3. Very good. All right. You already knew the sum rule. Okay, back to page 109. Back to page 109. It says that when you have a derivative of several functions added together, they could be added or subtracted. Repeat this after me. Not multiplied or divided.
Not multiplied or divided.
But
Added or subtracted.
okay. All right. So we do have a product rule later for multiplication, and we have a quotient rule later for division. But right now, when you have two or more functions just added or subtracted, then you take the derivative of each term, each particular function. So when you saw this problem, hopefully you said, okay, if I had the function 3x, you already knew that was a straight line anyway, the slope is 3. If I have a function y equal to 0, that's a constant, the derivative of a constant is 0. So the answer is the derivative is 3. All right, see if your friends learn from the red ink and use proper notation.
I did.
Okay, so I'll send around a blue pen to give yourself a big check if you learn from your mistakes. Okay, all right, everybody good? Third example. F of x is equal to 3x plus 1 squared. Talk to your neighbors about that.
This is a quadratic question.
Make it. Take it out.
Expand.
Whatever. I don't remember the word. So that is all addition.
Okay, I'm hearing good thoughts here. I can't hear the back row. What are y'all doing back there?
Working on it.
You're working on. That's a good answer.
And then basically just take it out. I don't remember all the shortcuts.
Okay, what's the concern here? What's the concern?
It's not just to the x, it's to the whole thing.
Exactly. So you knew to recognize we got a problem here, that it is not x raised to a power, but a function that's actually raised to a power. All right, so we are thinking, well, what can we do? And I heard some great brainstorming. This is squared. So you were thinking about expanding the product. So just change the appearance of the problem, but give the same problem. Let's multiply it out. How many thought to multiply that out, square it? Raise your hand. Oh, gracious, y'all are all good. Okay, that would be 9x squared plus 6x plus 1. All right, and then we're ready to take the derivative term by term. All right. It is so good that you recognized it did not fit the rule. It was not x raised to a power, but some function of x. All right, so if you take the derivative, just tell me what you got. 18x plus 6. How many got that right? Raise your hand. Let's be proud. I am proud of you. Excellent, excellent. Yeah, you're done. Life is great. All right. F of x is equal to the square root of 3x plus 1.
And then don't you no, you don't. Yeah, you can.
All right, what are we going to do here?
Or can we just square it?
3x plus 1 raised to half.
3x plus 1 raised to the
Half.
1/2.
Did that?
Then what are you going to do?
Don't know.
Say it again.
I don't know.
Right, we need some help here, don't we? It wasn't too bad when we had it squared, or even if we had it cubed. But if we'd had it to the 10th power, we would have not been oh so happy to multiply it out 10 times. And now that we have it raised to a 1/2 power, we don't know how to raise this to a 1/2 power. So we need help from another rule, don't we? Okay, well, here comes the next rule. Page 110 at the top. This is a rule that you want to highlight in red. You'll be working it to death the rest of the semester, summer session. It's called the general power rule. later, it's going to look a whole lot like what we call a chain rule. Some books just kind of skip over this and go right into what is called a chain rule, but we're going to call it a general power rule. If I put it in the middle, would that be easier to see? There you go. This is on page 110. Okay, now let's look what the general power rule says. It says that when you're going to take the derivative of a big old function raised to the r power, we've been doing x raised to the r. Now we have a function raised to the r. Well, when you first look at it, it almost looks like what we call the power rule. You brought the r down, you rewrote exactly, you decrease by 1. But we kind of chain on to that times the derivative of the function. We call that the derivative of the inside. So the general power rule says that when you have a function raised to a power, start out with that good old power rule. Bring the exponent down, rewrite exactly, decrease by 1, and don't forget to then multiply it times the derivative of the inside. This is the part right here that people get in a hurry and leave off, times the derivative of the inside. Okay? All right, so I want to go back now to the question where we had the problem squared, and we multiplied it out, but let's apply the general power rule, and then we'll go to our square root problem. Okay? All right, everybody see it? So you're just going to start out like the power rule. Bring the r down, rewrite how? Exactly. Let's try that again. You're going to bring the r down, you're going to rewrite exactly. What are you going to do to the exponent? Decrease by 1, and what are you not going to forget? Multiply by the derivative of the inside. Let's try that again. Don't look up here. All right, you're going to have a function raised to a power, so to take the derivative, you're going to bring the r down, rewrite.
Exactly.
Everybody say it. Bring the r down.
Exactly.
Decrease by 1.
Then multiply by.
Multiply by the derivative. Okay. I want you to rework this problem right now. F of x equals 3x plus, oops, let's turn the page over. F of x equals 3x plus 1 squared. And I want you to find the derivative using the general power rule. And mumble the rule as you do it, so you'll remember it. And don't forget that word exactly. All right, we're going to get the very same answer that we got when we expanded it. Everybody got it?
Yes.
All right, so we have a function raised to a power. General power rule says bring the 2 down. What does it say?
3x plus 1.
Rewrite how? Exactly. Decrease by 1
Multiply by.
times derivative of the inside. Okay, so 3 times 2 is 6. So we have 6 times 3x plus 1 to the first. This is perfectly great to stop right here. But because we're trying to make sure we got the same answer as before, if you expand the product, you get 18x plus 6. And that's what we got earlier. Okay? All right. Check your proper notation. Did anybody forget to multiply by the 3? Did you?
I didn't understand that part in the beginning. I get it now.
Okay, circle it in green, so that'll be a go. Don't ever forget that again. Oops, sorry. All right, so multiply by the derivative of the inside. Everybody got it? All right, now let's go to the next example I put up. F of x equals the square root of 3x plus 1. All right, so we have 3x plus 1 to the 1/2. Take a second and find the derivative. Do you have yours? Who's got it signed? Just put your paper up.
Where's you at?
Can I put your paper up?
Mine?
Yes.
Try.
Better than I'm doing.
Oh, this is my answer.
All right. And one of the reasons I want to do this is because we want to edit things now before a test time. All right, so here's the problem. Square root of 3x plus 1. What's that little square there?
Oh, that's nothing. That's nothing.
Okay. All right, so you rewrote your function as 3x plus 1 to the 1/2. All right, what's the first thing everybody's going to get excited over with this line? This line right here. What are you going to get excited about?
Negative 1/2.
Excited in a negative way.
This is a negative 1/2.
What's missing?
F.
All right.
I put that at
We got to use proper notation. You work all the way down. You make complete mathematical statements that are accurate. We don't go with sloppiness at NC State University. All right, so let's get our complete mathematical statement. You're saying the derivative is now equal to, you brought the 1/2 down, you rewrote exactly, you decreased it by 1, derivative of the inside. Okay, now let's see what happened from there.
That's 1/3 x.
Okay, so how did you go from 3x plus 1 to the negative 1/2, which is what that is right there?
Because I had a 1/3 x, and then it was plus 1/1. So I don't know.
All right, let's do our properties of exponents that you guys are supposed to be staying at home night working on. How do you deal with a negative exponent? Put it in the denominator, so that's 1/3x plus 1 to the 1/2, right?
But why is 1/2?
You got a negative exponent. The rule is a to the negative m is 1/a to the m.
Oh, sorry. I thought you moved the 1/2 into the front to the back.
Okay, yeah, I'm just trying to deal with this little part right here that I couldn't figure out what happened. All right, now, there's nothing else I can do with a square root of 3x plus 1, correct? All right, so this part right here caused us a few problems. So it's equal to, this is the derivative, 1/2 times 1/, if you want to use square root notation, that's fine, 3x plus 1 times 3. So your final answer should be 3/2 square roots of 3x plus 1. Okay, is that what you got?
Yeah.
Okay.
So,
So 3 is still in the numerator from right here. The 3 was correct. The 1/2 was correct. And something went a little bit crazy in there with that 3x plus 1 to the negative 1/2. You've got to use your properties of exponents.
Slight miscalculation.
Major miscalculation. All right, let's try another. Yes.
if we had in the beginning multiply the 3 by the 1/2, then can we have 1.5 in the numerator?
Question is, could this 3/2 be a 1.5? Yes. Yeah. Okay, everybody good? All right, let's try another one. Will you pass that paper back? And thank you for letting me use your paper because we want to learn from each other's mistakes and make corrections.
No problem.
All right, next example, find the derivative. Y equals 1/5x squared plus 1 raised to the 10th. Find the derivative. And I'm going to get somebody's paper on the back row this time, so write it neatly. And it's okay if you make a mistake now, just don't make it on the test. You got it? Okay. Let's see what you get. How'd you get a 19 out of that? If you'll do your little, Okay, life is looking great. Everybody's looking good. That problem was too easy. I'll have to come up with another one. All right, we're going to look at this work. Can you see it? All right. Just as when you had 1 over x to the 10th, it didn't fit the rule exactly, you have to rewrite it as the function raised to a power. So the 5x squared plus 1 had to be raised to the negative 10 power, using your properties of negative exponents. All right, now we have a function raised to a power. So the derivative, great notation here, the negative 10 is down. It's rewritten how? Exactly. Decreased by 1. Now sometimes people need to just go, okay, minus 10 minus 1, so you don't make any mistakes. Minus 10 minus 1, that's a negative 11. And then that's just like the power rule. But now we have to generalize more, multiply times the derivative inside. The derivative 5x squared is 10x. The derivative of 1 is 0, so we have it times 10x. So now negative 10 times 10x is negative 100x. The 5x squared plus 1 raised to the negative 11th means this is multiplication. We put it down in the denominator. What would y'all give this one? I'd give it a A plus.
5, 6 squared.
Okay, A plus. Anybody have a question on that?
I got it right.
How many did get it right?
I did.
Good, good. Well, here, give yourself a big A plus.
All right.
All right, anybody else question?
Wait, where did that 10x at the end of?
Where did this come from?
Yeah.
The 10x comes from derivative of the inside. The derivative of 5x squared is 10x. The derivative of 1 is 0. Derivative of a constant 0.
Oh, yeah.
Everybody got it? Okay, do you mind passing this all the way back? All right, let's do another example. Y equals, find the derivative. Y equals 1 over 5x squared plus 1. Actually, I'm going to make this a little harder.
Thank you.
Let's make this a 12x plus 3. It's not much harder. A little more interesting. Okay, I'm going to get somebody off the second row for this. 1 over 5x squared plus 12x plus 3. Think back, if you had 1 over x, how did you rewrite it before you took the derivative? 1 over x.
Negative.
To the negative what?
Negative power.
Which was a negative 1, right? If you had 1 over x and you got ready to take the derivative, it was to the negative 1 power.
Would you stop talking to yourself?
What are you you're always forgetting to say rewrite.
Oh, I'm just forgetting the do the whole thing on the inside, then put the derivative.
That's
on the
right.
outside.
Rewrite exactly. You're leaving out that little phrase, and that's why you're missing it each time.
Did you take the whole thing?
Okay. Yeah.
Just do 1 over this whole expression.
Well, that's the only thing with the negative exponent, correct?
So this stays on top.
Mm-hmm. All right, I'm going to take your paper up, so finished up, please.
I think this is right. I feel it in my heart. Deep in my heart.
And you lost that right there, so just put that out front.
What, the negative part?
Yeah, didn't you just recopy that?
Yeah.
Right.
I did. To take the derivative, I just made it negative before.
Oh, okay, so that's gone now? Okay.
If it's right, it's right.
So you don't get me when you go.
I know. Well, that's my job, though.
How did we just reach that?
See, there wouldn't be any challenges if you didn't get some little marks on here. Okay, let's look at this one and see if we want to edit anything to perfection. All right, here it is right here. Okay. All right, before you can take the derivative, it needs to be a function raised to a power, not 1 over the function. So the function was rewritten as f of x equals 5x squared plus 12x plus 3 raised to the negative 1. All right, so now it's going to fit my rule, a function raised to a power. Everybody did that correctly? All right, now we're ready to take the derivative. The rule says bring the negative 1 down front. I don't have my glasses on. Is that a negative 1 in there?
Yes.
Okay, equals. Don't forget your little equal signs. You're like making a complete statement. The negative 1 was brought down. What do we say here? Rewrite exactly. Negative 1 minus 1 is negative 2. And then what are we going to do? Derivative of the inside. What's the derivative of 5x squared? Okay, let's make that a 10x. And the derivative of 12x is 12. And the derivative of 3 is 0. Okay? Derivative 5x squared. Okay. All right. Now, it's only the factor of 5x squared plus 12x plus 3 that's raised to the negative 2 power. So carrying that down in the denominator made that to a positive 2 power. And now we have negative 1 times 10x plus 12. And that would make that a negative 10x minus 12. So he actually distributed the negative right here. If you're going to distribute it, though, be sure you mark it out so it doesn't move. All right, how many got that right? Raise your hand and make me feel good. All right, this side of the room is hot over here. What's happening over here? Not so hot, huh? All right, you have lots to practice with in your homework. But be sure before you start your homework, you pass that back, that you go back and write the examples down we did in class. Close your book. Do it yourself for practice. And the exercises has lots of problems. Page 116, 1.6. You got lots of problems to work using the power rule. Okay, lots of problems. The answers are in the back of your book. Drill and practice. I did the even, didn't I? Here's the odd. The odds are in the back of your book. All right. We are ready to move on now into limits. So we're in section 1.4. General power rule you gotta be good at. So you cannot work too much. Work, work, work. Okay? Work the even problems. I'll look at your work. All right. We're in section 1.4, and we're going to study limits first. Limits. Okay? And in your pre-calculus course here, if you took it at state, we introduce limits intuitively in that course so that once you get here, you're very good at it. So I'm going to first introduce limits to you by example and talk through it. Okay, I want us to look at y equals x squared. Y equals x squared. Okay, and the way we present it here in Pre-Calculus Math 107, I know, is we would say as x approaches something like 3, what does y approach? Did any of you take Math 107 here? Okay, do you remember these kind of words? If you did, yeah, you need to ask for a refund if your instructor didn't do that for you. Okay, all right, as x approaches 3, what does y approach? So you would go here on the x-axis. Approaching 3 means not equal to 3, but let 3 be like a magnet, and we're coming in around 3 from both sides. So as x approaches 3 from this side, here's that y value. As x approaches 3 from this side, by the way, this is called the left side of 3, and this is called the right side of 3. As you approach 3 from the right side, here's its y value. And as you keep getting closer and closer and closer to 3, the y value is getting closer and closer to what? 9. Y approaches 9. Okay? Now it just turns out that when x is 3, y happens to be 9. But we're saying as we get real close, so you would be putting numbers in like 2.9 on this side of 3, would be numbers like 2.999, 2.9999. As you're getting closer and closer, the y value is getting closer and closer to 3, but a little bit smaller in this case. And on the right side, you'd have numbers like 3.001, 3.0001. You're coming in closer and closer, and the y values are getting closer and closer to 9. Everybody got that? Remembers? Okay, so now we just use the new symbol for limits, and that tells us. This question right here would say, what is the limit as x gets very close to 3 from both sides? It says approaches 3. The word here is approaches, not equal to, but approaches, gets very close to 3. What is the limit as x gets real close to 3 of x squared? Well, x squared is the y value. So it's basically saying as x gets real close to 3, what does the y, which is x squared, get real close to? And everybody says 9. Okay? All right. Now, that sounds a little too easy and almost confusing because the limit is exactly equal to the y value. So let me make another example up real fast. Okay, this is example 2 by visual illustration here. The graph is going to go like this. And then we're going to pick it up. I don't know what the equations for this is. I'll just stick in some numbers. All right. This is where x is equal to, say, 2. And this little y value over here is about a 3. And this little y value up here, we'll just say is a 7. Okay? All right, so this is the graph of some made-up function. Some made-up function. All right, if I ask you, what is the value of this function at 2? That means when x is exactly equal to 2, based on my graph, what is the y value? An open circle means that's not included there. When x is, the solid dot means it's included. When x is exactly equal to 2, what is the y value? 7. Okay? Now, let's do limits. We're going to look at the limit as x approaches 2 of my function. This whole thing up here is my function. All right? Now remember, approaching 2 means you got to go to the left, and you got to go from the right, and it's got to approach the same value. All right, if I come up, and this is the notation, x approaches 2 from the left. We use a little minus sign there. That means take just a little itsy bit off of 2. So if I'm looking from the left of 2, or a little bit smaller than 2, that's this region right here. So if I'm very close to 2 on the left, what's the y value very close to? 3. If I look at the limit as x approaches 2 from the right of my function, 2 from the right is on this side. What is the y value getting very close to? 7. In order for the limit as x approaches a number to exist, when you come in from the left and from the right, it's got to go to the same number. What happened here when you came in from the right and left? Different numbers. So what do you bet we say about the limit of this function as x approaches 2? Does not exist. And we just usually use the symbols D, E, does not exist. D, N, E, does not exist. Because the limit from the left has to be the same value as the limit from the right. And when they're not equal, the limit does not exist. Okay? So limits, we're coming in from left and right. All right, I'm going to the book on page 101. Page 101 in the book. And we'll just look at each of these. We're supposed to determine visually if the limit exists at 3. Okay, so when x is 3, here's your function. We're on page 101. And when you get real close to 3 from the right side, it looks like the y value is getting close to 2. But if you come real close to 3 from the left side, where's this y value headed? Down to negative infinity. What would you say about the limit as x approaches 3 here? Everybody. Does not exist. Okay, let's go to problem 2. We're still looking around 3. We want to know, does the limit as x approaches 3 exist? So, okay, we come in from the left, and when you come from the left, the y values are getting very close to 2. You come in from 3 from the right, the y values are very close to 2. Would you say the limit exists here? Yes. What is the value of this function at x equal to 3? When x is 3, what is y in problem number 2 here? Nothing. It doesn't exist, does it? All right, so we have a limit that actually equals 2, but there's not a point there where x is equal to 3. Everybody getting the difference between what is f of 3? I'm going to just write in my book. F of 3, that says when x is exactly equal to 3, what's the y value? Well, that does not exist, does it? But if we take the limit as x approaches 3 of my function, everybody told me it had a value of 2 there. Okay? All right, let's go to problem number 4 at the bottom. 4. As x approaches 3, what would you say about the limit here? Does not exist. Why? The y values from the left and the right are different. If you're coming in from the left, the y value is 5. The limit from the right, the y value is 3. Since those two things don't equal, the limit does not exist. Everybody got it? All right, let's go to problem number 6. What would you say about the limit as x approaches 3 here? Okay, the very best answer would be to say the limit is positive infinity, because as you come in from the left and right, the curves are both headed in the direction of positive infinity. We know that positive infinity does not exist, but the question is, if they're going the same direction, help us out, tell us where it's going. Okay, so the best answer here is positive infinity. Again, infinity does not exist, so does not exist is not an incorrect answer, it's just not the best answer. Okay, everybody got it? All right, well, most things are not visual, as you'll see down here. So I have a little cookbook set of rules for you, and I'm going to illustrate by example. All right, you want me to call it cookbook? This is McCollum's Quick and Simple Cookbook. All right, and I'm going to illustrate by example. 1, we're going to do the limit as x approaches 2 of, what do I want to do? X plus 3. Okay. In your brain, you're probably not going to want to graph these each and every time. But you know that y equals x plus 3 is just a straight line. And you know it's defined for all values of x. And so as x gets real close to 2, what do you think the y value is getting close to? 5. So I call it the plug and chug. Plug and chug. We're just going to plug it and chug it, and if we get a number, then we're also happy because that's it. So this would be 2 plus 3 is 5, and 5 is the limit. You can visualize the graph, y equals x plus 3, come in real close to 2, and the y values are going to get close to 5. All right, so my first example is the first quick and simple rule. Plug and chug. Well, plug and chug is the rule. Plug and chug. And part A. If you get a number, then that's the answer. All right, we got a number, that's the answer. Okay, the second part to the plug and chug rule. We're going to have the limit as x approaches 2 of 1 over x minus 2. 1 over x minus 2. What happens when you plug and chug here? You get a number divided by 0, right? You get a 1 over 0. And we say that is undefined. So what do you bet that tells you about the limit? Does not exist. Rule number 2, which is B under my plug and chug, if you get a number over 0, and this number, by the way, is, I don't know how to tell you this in another color, number that's not equal to 0. In other words, this is not 0 over 0, but you get some other number over 0. Then your answer is going to be one of 3 things. Does not exist is always an answer. It's not always the best answer. Sometimes a better answer is positive infinity, as in our example number 6 that we just had. Because what's happening in this problem is we have a vertical asymptote. Vertical asymptote. Okay. Or another possible answer is negative infinity. All right. In our problem number 6, this was, if I were going to make up an answer, I would think this would be something like 1 over x minus 3 maybe squared. Because all your y values are positive. That's not exactly it though, because they got little parabolas there. So we'll just say it's approximately that. 1 over 0, when x is approaching 3, it gives you a 1 over 0, so that limit doesn't exist. But if you were on both sides of 3, the better answer to say is it's going in the direction of positive infinity. Okay, now let's look at our problem, the graph of it. 1 over x minus 2. Y equals 1 over x minus 2. We know this is a hyperbola, has a vertical asymptote at x equal to 2. Remember, you're shifting from Math 107. It looks like 1 over x shifted to the right 2 units, and the graph's going to look like this. You know when x is 0, y is negative 1/2. It looks like this. Okay? All right, so as you're approaching 2, the limit as x approaches 2 from the right and the limit as x approaches 2 from the left, if you're on the right side of 2, actually when you see a little plus or minus, it's asking you what is the direction. You know it's undefined at x equal to 2 that there's a vertical asymptote. So if you're on the right side of 2, you see it's headed to infinity. Now how do you do this without a picture? You know the answer is either positive or negative infinity, so a little bit bigger than 2 would be a number like 2.1. And the question is, if I put a 2.1 in for x, is this a positive or negative number? Positive. So it's headed to positive infinity. If you're a little bit smaller than 2, you would be putting in a number like, what's a little bit smaller than 2? 1.9. If you put a 1.9 in for x, is this expression positive or negative? Negative. So the limit from the right is headed to positive infinity. The limit from the left is headed to negative infinity. So when you answer this question, what is the limit as x approaches 2 for this function, your only answer you can give in this case is does not exist, because they're not both going the same direction on each side. Everybody got it? Okay, so cookbook number 2 was when you get a number that's not a 0 in the numerator over 0, it definitely is not going to exist because you don't have division by 0. But if they're going the same direction on each side, then the better answers are plus infinity or minus infinity. And the way I make you do this on a test is I usually put in a problem where you're doing a one-sided limit, because then that is asking you what's the direction. Okay? All right, third example. Limit as x approaches 2, and we have something like x squared minus 4 over x minus 2. X squared minus 4 over x minus 2. What happens when you plug and chug? You get 0 over 0. All right, that has a special name. It's called indeterminate. Yes, very good. Indeterminate form. You cannot determine. Oh, I'll put an R in there. I don't know why I did. Determinate. I-N-D-E-T-E-R. Gracious, I really did it bad. Indeterminate. Indeterminate form. Indeterminate form. You can't determine if the limit exists or not. That means you've got to change the expression, simplify the expression. So cookbook number C is when you plug and chug and you get 0 over 0. You're going to have to find a way to simplify. Okay? Find a way to simplify to see if you can do it. All right. Now, you were exactly right. That was good memory. Let's look at the function y equals x squared minus 4 over x minus 2. In pre-calculus, you were always asked, what's the domain? And when you had a function like this, you looked at the denominator for the domain, so x cannot be equal to 2. So your x is all real numbers. X is the element of all real numbers, except x can never be equal to 2. All right, so no matter, once I start playing around with the function to change its form, change its appearance, I have to hold on to the original domain. All right, and then I heard you say simplify because the numerator factors. So we'll have x plus 2 over x minus 2, difference of two squares. And the x minus 2's divide out. So this function, y equals x squared minus 4 over x minus 2, simplifies down to y equals x plus 2, but I must hold on to the original domain. Anytime you simplify something, you can't go change the domain. It has to be the original domain in the function. So if you were graphing this problem, y equals x plus 2, the y-intercept is 2, slope is 1. Okay? But this says you better leave out where x is equal to 2. So where your x is equal to 2, you just come up here and put a little hole in it. And where that little hole is over here at 4. So it's a straight line with a hole in it. Okay, the graph of that function that looks awful is no more than a line with a hole in it. Okay, so now you will be looking at for this problem, the limit as x approaches 2 of x plus 2. Now the reason I'm only using the x plus 2 is because the words are approaching 2, not equal to 2. So this function, whenever it is not equal to 2, is this. So therefore I can use this, x plus 2. Everybody got it? So as x approaches 2 of this function, this sends us back up to part A now. When you plugged and chugged, 2 plus 2 is 4. The visual on this says as you approach 2 from the left and from the right, the y value got close to 4, although that point does not exist. Everybody got it? All right. You get lots of homework problems on page 101, and if you follow the 3 rules I just gave you, where you always plug and chug, if you plug in and you get a number, then that really means that you have a little continuous function there. The y value is the same as the limit when you plug and chug and get a number. If you get a number over 0, that's undefined, so the limit cannot exist. You're just going to check on both sides to see if they're going the same direction or opposite directions. If you get 0 over 0, such as probably in problem number 17, I'm looking right there. If you plug in 0 for x, you're going to get 0 over 0. So you're going to 0 over 0 simplify, and that would be by factoring the x out of the numerator and dividing out. Because you're not equaling 0, you can divide. Let me just do number 17, because sometimes seeing is better than hearing. We have the limit. This is 17. I'm going to write it down real fast and then I'll move the book. 17 is the limit as x approaches 0 of x squared plus 3x over x. When you plug 0 in for x, you're going to get 0 over 0. What form did I say that is? Indeterminate. I can't determine if the limit exists or not. I need to change its appearance. All right, so I'm going to factor x out of the numerator. Now, I can divide out the x over x because x is not equal to 0 because we're only approaching 0. X is some other number other than 0. It's like 0.01 or negative 0.001. So I can divide x over x out because they're not zeros. And now I'm left with the function x plus 3. So this function that we originally started out with, x squared plus 3x plus x, is the function x plus 3 as long as x is not 0. Okay, and we are approaching 0. So now I plug and chug and I get 3 and Yay. All right, everybody got it? Okay. When we can come back to the book here, problem number 21, you can probably look at that and see that when you substitute in, you're going to end up with a 0 over 0. So you're going to have to simplify by factoring. Probably the same thing with problem number 23, and probably a number over 0 is going to happen in number 25. I can already see that because you'll have 64 plus 64 over 0. So you know that's not going to exist. So you're just going to check real close to 8 on both sides, such as 7.9, 8.1, just to see is it positive or negative, which direction it's going to go. And if they go opposite, then you say does not exist.
For 21, you'd end up with x plus 4 and x minus 4 on the top. And then how would you...
Okay, this question is actually on WebAssign, similar. Okay, let me ask you this. Suppose I have x minus 2 over 2 minus x. How do I simplify this expression? It's not the same thing. If you put a 3 in, you'd get 3 minus 2 over 2 minus 3. How are they different? One's negative, one's positive. So how can I, they look the same, but they're not quite exactly the same. So how can I rewrite the denominator so I can divide out?
Minus of.
Factor out a negative 1, and that would give me negative 2 plus x, right? And x minus 2 and x minus 2 are the same thing. And now we have 1 over negative 1, which is negative 1. You can always double check things. Just pick a number like x equal to 10. If you put a 10 in here for x, you get 10 minus 2 over 2 minus 10, 8 over negative 8, which is negative 1. Okay? All right, make yourself a little note on that. I know there's a WebAssign question with that, and I know that does appear on some tests too. Good question. Good thoughts looking ahead. All right, lots of examples with limits. Well, the whole reason we do limits is so that we can get to the limit definition of the derivative. You will definitely have one question on your test, limit definition of the derivative. Limit definition of the derivative. And I forgot what page I told you that was on. Something like 87? Yes, page 87. All right, well, when you look at it from a distance, it looks pretty awful, but I'm going to give you a visual on it and tell you where it came from, and then it'll be nice. Okay, we're on page 87, and this is actually in section 1.3. The rules that have already been given for the derivative, they come from people long ago with feather and ink by candlelight. Use the limit definition of the derivative to formulate the rules. That's where your rules are coming from. This you will need to memorize and know how. The derivative is the limit as h approaches 0, f of x plus h minus f of x over h. It looks awful till I'm going to explain it to you, and then it'll be easy. It looks like, what'd you learn it to be, this part?
A difference quotient.
Okay, in pre-calculus course here at State, you get a lot of practice with f of x plus h minus f of x over h. That's the difference quotient. I'm going to bring that back in as I explain it to you, and then tell you why we take a limit as h goes to 0. All right, so good. Had practice from pre-calculus in that. All right. Okay, so I'm going to give you a visual of what's going on here. Okay, we're going to have a curve. And what we want to know is what is the slope of this curve at the point x. And instead of calling it y, I'm just going to call it f of x. You know, a point is the ordered pair x, y. But because I'm trying to get to my definition here, I'm going to call it x, f of x. And we know that when we want the slope of a curve, slope means I need 2 points, right? Slope, difference in y's over difference in x's, change in y's over change in x's. So what I'm going to do is just really blow this up, but I'm picking a point very close to this, but this is greatly blown up right here. Okay? And this point, okay, here's my little x from here. I'm going to come over what is called h units. I'm going to come over h units. So this point, the x value will be x plus h. If this number were 3 and I were going to go over 0.1 to get real close to it, then the next point would x value be 3.1. H is how far I'm moving over to get to the next. Everybody good on that? So what would we call that y value there? F of x plus h. All right, so here we have f of x. Up here we have f of x plus h. That's that y value. And this x value right here is x plus h. Okay? Now, when I draw a line through those 2 points, I don't have a good old red one. Anybody got the red? All the reds ended up on the, you can throw it, just don't hit me in the head. Good, I'm glad, because I would have missed it and then I'd been embarrassed. Okay, I'm going to draw a line through those 2 points. A line through those 2 points. This particular line through any 2 points on a curve has a special name. It is called a what kind of line? Secant line. This is secant line. A line through any 2 points on a curve is called a secant line. All right, now we're going to get the slope of the secant line. Slope of the secant line. Well, slope means differences in the y's. So we have f of x plus h minus f of x. All I did was get the difference in the two y values divided by the difference in the two x values. So that's an x plus h minus x. Right? All I've done is found the slope between 2 points. Now let's clean that up a little bit. That's f of x plus h minus f of x. And what's left in the denominator when I clean it up? H. All right. So all I've done is found the slope of the line between 2 points. All right, let's go back to this little definition right here. This part is f of x plus h minus f of x over h. That is the slope of the secant line between 2 points on the curve, right? Okay, but our job is to look for a derivative. A derivative is the slope of the tangent line. That is the line that best fits the curve at that point. So what happens is we don't want a h to be too far away. We want the h to be really teeny, teeny, tiny. We want those 2 points sitting on top of each other almost to come up with our tangent line. So this is magnified a zillion times. Okay, this is really magnified a zillion times. So we're going to let our h approach 0. The distance between those two x values are right on top of 0. You have 3 and you have 3.0000001. That's pretty close, wouldn't you say? And the way we do that now, instead of calling it a secant line, because we're trying to get a line that best fits, we'll have a slope of a tangent line. And we're going to do that by taking the limit as h gets real close to 0, the distance between those two x values, of f of x plus h minus f of x over h. We know the slope of the tangent line is the same thing as the derivative. Okay? Pretty neat, huh? All right. Let's do an example so you can start playing in your homework, having a great time. So it's the slope of the secant line, but we let those 2 points get right on top of each other by letting the distance between those 2 points approach 0. And that will be our derivative. All right, here we go. We're going to start out with an example that we already know the answer to. Okay, the instructions on the test. Use the limit definition of the derivative. And when you see this, that says 0 credit for rules. All right, when you see limit definition of the derivative, you got to use the limit definition of the derivative. I'm not asking you to use rules to find the derivative. To find f prime of x given, all right, we're going to go easy for right to begin with. F of x equals x squared plus 3. All right. If you were going to get 0 credit for using the rules, what's the answer? 2x. All right, that would be 0 credit if that's all you did on the test for a question that says use the limit definition. All right, so we remember that the limit definition is the limit as h approaches 0, f of x plus h minus f of x. That's just difference in the y's over the difference in the x's, and that simplifies down to a h. You could actually put down x plus h minus x and then simplify it yourself. All right, now all we're going to do is substitute in here everything that's appropriate, and life is great. All right, now we're going to have to find a f of x plus h. We know that f of any element is going to be that element squared plus 3. For example, if you wanted f of 4, wouldn't it be 4 squared plus 3? F of m would be m squared plus 3. F of x plus h will be, where, that's right, where you have those little parentheses, you're just going to put in the little x plus h right there. Okay, just like if you were finding f of 4. So when I square that, I get x squared plus 2xh plus h squared. Square x plus h times x plus h. X plus h times x plus h. X squared plus 2xh plus h squared. And then we have plus 3. All right, so now we're ready to substitute in everything we have. We have the limit as h approaches 0. In the place of f of x plus h, I'm going to write x squared plus 2xh plus h squared plus 3. And I use parentheses, and I encourage you to do the same thing. You'll not lose negatives if you do that. All right, then we have a minus right here, minus. And then f of x is our original problem, correct? F of x, so we'll go minus and use your little parentheses there again, x squared plus 3. Ooh, I'm about to run out of space there. And all of this is over h. Okay? All right, let's clean that up a little bit. We have the limit as h goes to 0. All right, we have an x squared, but if we distribute our negative, what's going to happen here to our x squares? Okay, they're going to cancel out, right? X squared minus x squared, and that's old happy day. Knock those out. See anything else that's going to cancel out?
3.
Okay, we got a 3 and a minus 3 going to cancel out. All right, let's see what we have now. We have 2xh plus h squared over h. 2xh plus h squared is all that's left in the numerator over h. All right, now we're going to McCollum's cookbook. Plug and chug. What do you get?
0 over 0.
0 over 0. What are you going to do? Simplify. All right, we're going to factor the numerator. What are you going to factor out? H. H is approaching 0, not equal to 0. So they divide out. I have the limit as h approaches 0 now of 2x plus h. Okay, what's McCollum's rule? Plug and chug. You're going to plug 0 in for what?
H.
H. When I plug a 0 in for h, that h goes to 0, and what am I left with? 2x. Is that the derivative of x squared plus 3? Yes. Are you not thankful for those guys that used pen, little feathers and ink and candlelight and stayed up late figuring these rules out for you? Definitely appreciative. Anybody know who did all that? I think it was Newton. I think it was Newton that did it. Okay. Start playing around with that. Clearly, we will pick up with more of this tomorrow. I did not get to the section on continuity and differentiability, but I'll get all that cleaned up tomorrow and keep moving. Have a great day, everybody.